Modern AI models convert complex files into high-dimensional vectors. This process mathematically maps out meaning, ensuring related concepts group together in high-dimensional space. But searching through that math breaks traditional databases. A standard B-tree index relies on a natural sequence, so numbers and letters can be sorted linearly. Vectors have no inherent order. There's no mathematical reason to put a beach photo sequentially before or after a food photo. Instead of scanning for exact matches, systems use approximate nearest neighbor search. This finds vectors that sit close to each other in multidimensional space, accepting a tiny fraction of lost accuracy for a massive leap in speed. To pull off that speed, popular graph-based algorithms like HNSW require enormous memory overhead. They operate on the assumption that the entire index graph can be loaded into RAM on a single isolated machine. That assumption collapses in a distributed SQL environment. When data is spread across global regions and machines must survive hardware failures, a monolithic, memory-hungry graph structure becomes a point of failure. But CockroachDB operates under strict distributed rules. The database is built to scale linearly across multiple regions and guarantee complete transactional consistency, even if entire hardware racks fail. To build a vector index here, the engineering team set 6 rigid parameters. First, there can be no central coordinator node. Second, the index must live entirely on persistent disk storage. And third, queries must require minimal network hops between nodes. The remaining 3 rules focus on operating at scale. The index must be sharding compatible, avoid creating traffic hotspots, and process updates in real time without blocking foreground queries. These 6 strict requirements immediately disqualify almost every popular off-the-shelf vector algorithm available today. Building a vector search that survives within a distributed SQL system required the team to abandon monolithic designs and engineer C-SPANN from the ground up. C-SPANN is built on a hierarchical k-means tree. This evaluates raw data, grouping mathematically similar vectors into distinct partitions. Inside each partition are dozens to hundreds of vectors. The central point, the centroid, acts as their mathematical center of mass. Those base-level centroids are then grouped themselves. They cluster into higher-level partitions, forming a tree structure that terminates at a single root node. When a search query comes in, it trickles down from that root. The system calculates the distance to the centroids at each level, choosing to descend only into the specific partitions that match the query. The tree is designed with a fan-out ratio of approximately 100. This creates an extremely wide, shallow data structure, rather than a deep, complex web. At that width, an index containing 10 billion vectors requires a maximum of only 5 search levels to reach the leaf nodes. This predictable, shallow depth guarantees minimal network round trips. No matter how large the dataset grows, query latency remains low, satisfying the core distributed constraint. Next, the team mapped this tree structure directly onto CockroachDB's standard key-value storage layer. Every partition in the k-means tree is stored as a self-contained contiguous set of rows, making the index naturally sharding compatible. The core database engine is unaware it is managing an AI vector indexed. It simply sees these partitions and treats them as ordinary table rows. Because the index is treated as standard data, the system automatically routes frequent reads through its existing block cache, avoiding custom RAM allocation logic. As the physical cluster expands, the storage ranges holding those partitions are automatically replicated and distributed to the new nodes by the existing storage engine. By utilizing the database's native row handling, C-SPANN inherits enterprise-grade sharding, persistence, and fault tolerance entirely for free. Static indexes decay as vectors are constantly inserted or deleted. Partitions naturally swell or shrink, which can degrade search quality over time. When a partition exceeds its size limit, C-SPANN triggers an automated background split using a balanced k-means algorithm. The original vectors are divided into 2 roughly equal groups, and the routing tree is updated to point to the 2 new centroids. To maintain strict accuracy across these boundaries, the system uses nearest partition assignment, a technique derived from the SP-fresh algorithm. Immediately after a split, vectors near the border of a new partition mathematically evaluate their distance to all nearby centroids. If a vector realizes it is now mathematically closer to a neighboring partition centroid than its newly assigned one, it migrates to the better fit. All of these splits, merges, and border reassignments occur continuously in the background without blocking foreground transactional queries. This continuous cycle of micro-rebalancing eliminates the need for the massive system-halting index rebuilds common in other vector databases. Even a balanced structure faces a hardware bottleneck. 1 billion full-precision embeddings require 3 terabytes of disk space, creating a massive hurdle for search speed. To reduce this footprint, C-SPANN uses an aggressive compression methodology called RaBitQ quantization. The algorithm targets each 1,536-dimensional vector and mathematically reduces every single dimension down to a single bit. This is achieved through a random orthogonal transform to spread out data skew, followed by mean centering the vector against its local partition centroid. A standard 3 kilobyte vector shrinks to roughly 200 bytes, a 94% reduction in total size. This extreme quantization is inherently lossy, meaning distance estimates calculated on the compressed bits are only approximate. To compensate, C-SPANN uses a 2-stage re-ranking pipeline. It runs ultra-fast SIMD filtering on the compressed bits to find candidates, and then fetches the original full-precision database rows to calculate the exact distances. This pipeline absorbs the quantization error, delivering exact distance accuracy while maintaining the extreme speed of a compressed index. In production, the vast majority of vector searches are strictly scoped to a single tenant, user, or organization. CockroachDB handles this by introducing prefix columns. When creating the table, a user ID can be injected straight into the vector index definition. By declaring that prefix column, C-SPANN maintains a completely separate, isolated k-means tree for every distinct user in the system. A query executed by one user only scans their specific subset of partitions, structurally preventing cross-tenant data leakage and eliminating wasted compute. Search latency therefore scales with the number of vectors owned by that specific user, not the total size of the global database. Splitting a billion-vector database across millions of these isolated microtrees guarantees low-latency search regardless of how large the total application scales. This prefix routing logic also extends to physical geography through CockroachDB's regional by row functionality. Injecting a region column automatically partitions the vector k-means tree by global location. A European user's vectors and index partitions are stored and computed exclusively on European hardware. This regional co-location guarantees fast local search access while ensuring compliance with international data laws. The engineering team successfully met all 6 distributed architectural constraints without relying on external graph-based ML plugins. The architecture of C-SPANN proves that billion-scale vector indexing is achieved by integrating search logic into a distributed storage engine that handles sharding, replication, and persistence by default.